Hey there, future ML rock stars. Welcome back to the channel. Today we're diving deep into the foundational concepts that'll make you absolutely unstoppable on the AWS Machine Learning Engineer Associate exam. That's the MLA-C01 for those keeping track. Now, I know what you're thinking, another ML exam prep video? But hold up, this isn't your typical dry technical snooze fest. We're going to explore how your brain literally inspired the AI revolution, decode the mysteries of transformers, and master AWS services that are reshaping entire industries. Exam tip number 1. The MLA-C01 exam has 65 questions, 170 minutes to finish, a passing score of 720 to 1,000. But here's the kicker. This exam is heavy on SageMaker, with real hands-on scenarios. So buckle up. Let's start at the beginning. Your brain before GPUs, neural nets, and cloud clusters, we looked at the most powerful learning machine ever created, your brain. Neural networks are loosely inspired by the way your brain processes and passes information between neurons. Each artificial neuron in a neural net takes input, processes it, and passes it to the next layer, just like your brain's synapses. This biological inspiration laid the groundwork for everything from convolutional neural networks in computer vision to transformers in NLP. In the next sections, we'll break down how foundational neural concepts became scalable on AWS, the role of transformers in modern ML, the AWS services you'll need to master for MLA-C01 success. Stay sharp, we're just getting started. Picture this. Billions of years of evolution crafted the most sophisticated computing device in the universe, and it's sitting right between your ears. Deep learning isn't just some fancy computer science concept. It's literally modeled after how your brain works. In your cerebral cortex, you've got around 86 billion neurons connected by trillions of synapses. Each neuron is basically a tiny decision maker that fires when it receives enough input signals from its neighbors. Sound familiar? That's exactly how artificial neural networks work. Here's where it gets fascinating. Your cortex is organized in these mini columns that stack into hypercolumns, processing information in parallel. And guess what? This is remarkably similar to how modern GPUs process data. Evolution figured out parallel processing millions of years before Silicon Valley even existed. As exam tip number 2. When you see questions about parallel process distributed training on AWS, remember this biological inspiration. SageMaker's distributed training capabilities mirror how your brain naturally processes information. But here's the thing. While individual neurons are simple, when you connect layers of them together, magic happens. They start recognizing patterns, making predictions, and essentially learning from experience. This is the core principle behind every neural network you'll encounter in your AWS ML journey. Now let's translate this biological marvel into the digital realm and see how we build artificial neural networks that can recognize your face in photos, translate languages in real time, and even generate human-like text. All right, let's build some digital brains. Deep neural networks, or DNNs, are like digital versions of your cortex, multiple layers of interconnected nodes, each with weights and biases that determine how strongly they respond to inputs. But here's where things get spicy: the activation functions. These are the secret sauce that makes neural networks actually, well, intelligent. Activation functions, the personality of your neurons. Think of activation functions as the personality types of your artificial neurons. Let me introduce you to the family. Sigmoid and tang. These are the smooth operators. They scale outputs nicely, 0 to 1 for sigmoid, -1 to 1 for tanh. But they have a dark secret, the dreaded vanishing gradient problem. When values get too high or low, learning slows to a crawl. tanh is generally the better choice between these two. ReLU rectify linear unit, the simple but effective choice. Super fast to compute, which is why it's everywhere. But watch out for the dying ReLU problem. It can become linear for negative inputs and just give up learning. Exam tip number 3. For SageMaker built-in algorithms questions, remember, start with ReLU for most cases, use tanh for RNNs, and Softmax for final classification layers. Leaky problem solver. Fixes the dying ReLU issue by adding a tiny slope for negative values. Smart. Swish. Google's deep network specialist shines in those really deep networks with 40+ layers. Softmax, the decision maker, converts outputs into probabilities for classification. Perfect for when you need to pick one category out of many. Neural network architectures. Now, let's talk about the different types of neural networks you'll encounter in AWS land. Feed-forward networks, the straight shooters. Information flows in one direction, no loops. Simple but effective for many tasks. Convolutional neural networks, CNNs. The vision specialists, CNNs are absolutely brilliant for anything visual. They're inspired by your visual cortex and work by using local receptive fields. Basically, they look at small patches of an image and gradually build up understanding of more complex features. Here's the beautiful part. They're feature location invariant. That means whether a stop sign is in the top left corner or bottom right of an image, a CNN will still recognize it as a stop sign. The typical CNN pipeline looks like this. Conv2D layers. Extract features like edges and shapes. Max pooling 2D. Reduce dimensions to prevent overfitting. Dropout. Randomly forget some neurons during training. Flatten. Convert 2D feature maps to 1D for final decision. Dense. Dropout. Softmax. Make the final classification. Exam tip number 4. In SageMaker, you'll often see CNN architectures like ResNet for image classification tasks. ResNet uses skip connections to train very deep networks without vanishing gradients. Famous CNN architectures you might encounter: LeNet-5, the grandfather of CNNs; AlexNet, the breakthrough that started the deep learning revolution; GoogleNet introduced inception modules for efficiency; ResNet enabled training of extremely deep networks. Now, what if your neural network needs to remember things? Like understanding the context of words in a sentence, or predicting tomorrow's stock price based on historical trends. Enter recurrent neural networks, the memory masters of the AI world. RNNs have this beautiful feature called memory cells, where the output at one time step feeds back into the network at the next step. It's like having a conversation where each word builds on the previous ones to create meaning. RNN topologies, different flavors of memory. Sequence to sequence, perfect for machine translation, English sentence, French sentence. Sequence to vector, great for sentiment analysis, tweet, positive, negative. Vector to sequence, ideal for image captioning, image, text description. The training challenge, but here's where RNNs get tricky. Training them is like trying to teach someone a language while they're running a marathon. We use backpropagation through time, which can lead to the vanishing gradient problem we mentioned earlier. Imagine trying to remember the first word of this video by the time we reach the end. That's essentially what RNNs struggle with in long sequences. Exam tip number 5. When you see time series forecasting or sequential data questions in the exam, think RNNs. Amazon Forecast often uses RNN-based models under the hood. LSTM and GRU, the memory upgrades. LSTM, long short-term memory. These are like upgraded RNNs with both short-term and long-term memory banks. They use gates to control what information to remember, forget, or output. Think of them as having selective amnesia. They remember important stuff and forget the noise. GRU, gated recurrent unit, the simplified cousin of LSTM that performs almost as well but with fewer parameters. Sometimes simpler is better. But wait, there's a plot twist coming in our story. Okay, this is where things get really exciting. Remember how RNNs process information sequentially, one word at a time? Well, some brilliant researchers at Google asked, what if we could process all words at once and still understand their relationships? And thus, the transformer was born. The paper was literally called "Attention is All You Need," and they were absolutely right. From sequential to parallel. The game changer. Traditional RNNs are like reading a book word by word, never allowed to skip ahead. Transformers are like having a photographic memory. They can see the entire page at once and understand how every word relates to every other word. This parallel processing capability means we can train on massive datasets using modern GPUs efficiently. And that's how we entered the era of large language models. Self-attention, the magic mechanism. Self-attention is where the real magic happens. Here's how it works. Query key value matrices. Each word gets transformed into 3 different vectors, like giving each word 3 roles. Attention scores. The model calculates how relevant each word is to every other word in the sequence. Weighted combinations. Words with high relevance get more weight when forming the final representation. It's like being at a noisy party and knowing exactly who to focus on in the crowd based on context. Multi-headed attention means we do this multiple times in parallel. One head might track syntax, another meaning, another long-range dependencies. Exam tip number 6. When working with Amazon Bedrock or SageMaker Jumpstart, you're often dealing with transformer-based foundation models. Understanding attention mechanisms helps you choose the right model and architecture for your use case. Large language models. The transformer children LLMs like GPT, Claude, BERT, and Amazon Titan are all based on transformer architectures. They've been trained on enormous datasets to predict the next word, which enables them to generate coherent, useful, and even creative responses. Input processing pipeline. Tokenization, converting text into numerical tokens. Token embedding, mapping tokens to high-dimensional vectors. Positional encoding, injecting information about word order. Transformer layers, where all the attention and learning magic happens. Output processing, the model produces probability distributions over the vocabulary. Temperature, controls creativity. Low equals deterministic, high equals random. Top K, top P sampling filters token choices to improve response quality. Key LLM concepts for the exam. Context window, number of tokens the model can remember. Max tokens, combined input plus output limit. Foundation models, pre-trained models, e.g. Amazon Titan, Jurassic 2, that you can fine-tune or prompt engineer for specific tasks. Transformers changed everything. They're fast, powerful, and form the foundation of nearly all cutting-edge NLP systems you'll encounter in AWS today. Here's a beautiful truth about modern AI. We don't need to reinvent the wheel every time. Transfer learning is like standing on the shoulders of giants. We take models that have already learned general knowledge and fine-tune them for specific tasks. Think about it this way. If you wanted to become a chef, you wouldn't start by inventing cooking from scratch. You'd learn basic techniques first, then specialize in your favorite cuisine. That's exactly what transfer learning does. Foundation models. The AI foundation models are massive, pre-trained transformer models trained on huge datasets. These models often have hundreds of billions of parameters and are designed to be adapted for many downstream tasks. In the AWS ecosystem, examples include Amazon Titan, AWS's proprietary models for text generation and embeddings. Claude, available via Amazon Bedrock, optimized for conversation and reasoning. Jurassic 2, large-scale text generation. Stable Diffusion, for image synthesis. Llama, Meta's open-source family of LLMs. Exam tip number 7. Know the difference between SageMaker Jumpstart, used for training, tuning, and deploying pre-built models. Amazon Bedrock, used for direct API access to foundation models with no infrastructure to manage. Fine-tuning strategies. When adapting a foundation model to your specific task, AWS gives you multiple options. Continue training. Feed in your domain-specific data with a low learning rate to preserve general knowledge. Add new layers. Freeze the base model and add task-specific layers on top. Full retraining. Start from scratch. Rarely needed unless you have very large data and compute. Use as is. Many models are powerful enough to solve tasks without fine-tuning. Model zoos, platforms like Hugging Face, act as marketplaces for pre-trained models. AWS integrates seamlessly with Hugging Face, letting you fine-tune directly in SageMaker, deploy with pre-built containers, use thousands of state-of-the-art models for NLP, vision, and more. Transfer learning is one of the most powerful tools in your AWS ML toolkit. It lets you deliver value fast with minimal data while standing on top of world-class AI research. All right, now let's talk about the art and science of making your neural networks actually work well. Training neural networks is like tuning a high-performance car. Get it right and you'll fly. Get it wrong and you'll crash and burn. Learning rate, the Goldilocks problem. Learning rate controls how big a step your model takes while searching for the optimal parameters. Too high, you'll overshoot the optimal point and bounce around. Too low, you'll converge slowly or get stuck in a local minimum. Think of it like learning to drive. Start too aggressively and you'll crash, too cautiously and you'll never get anywhere. Batch size, the social learning effect. Batch size defines how many training samples your model processes before updating weights. Small batches, more noisy but may help generalization, like learning from one-on-one conversations. Large batches, more stable gradients, faster computation, like learning from lectures. Regularization, preventing the know-it-all problem. Overfitting is when your model memorizes the training data but fails to generalize. Regularization helps your model stay humble. L1 regularization, lasso, drives some weights to zero, performs automatic feature selection, used for sparse models. L2 regularization, ridge, penalizes large weights, keeps all features but tempers their influence, produces denser models. Exam tip number 8, SageMaker's linear learner supports both L1 and L2 regularization. Understand how these affect your model performance. Dropout, randomly disables neurons during training, prevents codependence between layers. Good for deep networks. Early stopping, stops training when validation accuracy stops improving, prevents overfitting and saves compute time. Gradient problems, the training nightmares, 2 common issues that plague deep neural networks. Vanishing gradients. Gradients become too small during backpropagation. The model stops learning in early layers. Exploding gradients. Gradients grow too large, making the model unstable or causing NANs. Solutions. Use ReLU instead of Sigmoid or TAND. Implement residual connections, e.g. ResNet. Use LSTM GRU for long sequences. Apply gradient clipping to control excessive updates. Training deep models isn't just about feeding in data. It's about striking the right balance between speed, stability, and generalization. Understanding these concepts is essential to choosing the right configuration in SageMaker or answering tricky scenario-based questions on the exam. You've built your model, trained it beautifully, but how do you know if it's actually good? Accuracy alone is like judging a chef only by how fast they cook. It doesn't tell the whole story. Beyond accuracy, the full picture. Let's break down the confusion matrix. True positives TP, correctly identified positives, false positives FP, incorrectly flagged as positive. True negatives TN, correctly identified negatives, false negatives N, missed positive cases. The metric family, recall sensitivity, how many actual positives did we catch? Recall equals TP plus FN. Useful when missing positives is costly, e.g. cancer detection. Precision, of all positive predictions, how many were right? Precision equal TP plus FP. Useful when false positives are expensive, e.g. email spam filters. F1 score, the harmonic mean of precision and recall, balances both concerns, good for uneven class distributions. Exam tip number 9. SageMaker Clarify can analyze both model performance and fairness metrics. Know when to choose metrics like precision, recall, or F1 based on your use case. Hack ROSI and PR curves, the visual truth. ROC curve plots true positive rate versus false positive rate. Ideal models hug the top left, area under curve. Times 1.0 equals perfect, 0.5 equals random guessing. Precision recall curve, better for imbalanced data sets, more sensitive to false positives. For regression problems, RFWID, R squared, proportion of variance explained by the model. RMSE, root mean squared error, penalizes large errors more, good when big mistakes are worse. MAE, mean absolute error, penalizes all errors equally, more stable and interpretable. Choosing the right evaluation metric depends on the business context, the risk of errors, and the type of model, classification versus regression. Don't just memorize, understand when to use each one. Ensemble learning, the power of teamwork. Why rely on one expert when you can have a team? Ensemble learning combines multiple models to make better decisions than any single model could alone. It's like having a panel of judges instead of just one. Bagging, parallel wisdom. Bagging creates multiple training sets by random sampling with replacement. Each model trains independently, then they vote on the final decision. Random forest is the superstar example. Hundreds of decision trees, each looking at different aspects of the data, then voting democratically. Benefits: reduces overfitting, easy to parallelize, works great out of the box. Boosting: Sequential learning. Boosting is like learning from your mistakes. Each new model focuses on the examples the previous models got wrong. XGBoost is the champion here. It's won countless machine learning competitions. Benefits. Often achieves higher accuracy than bagging, great for complex patterns. Exam tip 10. Both Random Forest and XGBoost are available as SageMaker built-in algorithms. Choose Random Forest for simplicity and interpretability, XGBoost for maximum performance. Deploying a model is just the beginning. In production, you need to monitor for data drift, model performance degradation, and security threats. It's like being a doctor for your AI systems. SageMaker Model Monitor. Model Monitor automatically detects when your model's performance starts degrading. Data Quality Monitoring. Detects changes in input data distribution. Model Quality Monitoring. Tracks prediction accuracy over time. Bias drift monitoring ensures fairness across different groups. Feature attribution drift monitors changes in feature importance. Security best practices. ML security involves multiple layers. Data security, encryption at rest and in transit, VPC endpoints for private communication, IAM roles with least privilege, model security, private Docker containers, network isolation, audit logging with CloudTrail. Exam tip number 13. Know the difference between SageMaker execution roles for training inference and user roles for studio access. Understand VPC configurations for enhanced security. All right, future ML engineers, we've covered a lot of ground today, from the biological inspiration of neural networks to the cutting-edge world of transformer models and AWS services. Final exam strategy. Key exam reminders. 65 questions, 170 minutes, 721,000 to pass. Heavy focus on SageMaker services and real-world scenarios. Hands-on experience is crucial. Use the AWS free tier. Understand the ML lifecycle. Data prep, training, deployment, monitoring. Study focus areas. Data preparation, 28%. SageMaker Data Wrangler, feature store, model development, 26%. Built-in algorithms, hyperparameter tuning. Deployment and orchestration, 20. Endpoints, pipelines, CI/CD. Monitoring and security, percent. Model monitor, CloudWatch, IAM. Your next steps. Get hands-on experience with SageMaker Studio. Practice with new question types. Multiple choice, matching, ordering, case studies. Focus on real-world scenarios, not just facts. Join the AWS community, forums, documentation, and practice exams. This certification isn't just about passing a test. It's about joining the ranks of professionals building the AI-powered future. The demand for ML specialists is expected to grow by 43% in the coming years. You're placing yourself at the forefront of this revolution. Thank you for joining this deep learning journey. Until next time, keep learning, keep building, and remember, the best way to predict the future is to create it with AI. All right, folks, that's it for today. If you enjoy Wisdom Bird Talks Tech, don't forget to like, bookmark, and share. Your triple support is the biggest motivation for Wisdom Bird to keep going. Got a tech topic you want to hear about? Drop it in the comments. Wisdom Bird will cover it next time. See you in the next episode, where we'll keep chatting tech, talking people, and exploring the human warmth behind AI. I'm Wisdom Bird, the super smart bird flying with you on this tech journey.